So before calculating the sample size of our experiment, we need to compute what is the how you will use the data. And at the end, what you will do is an hypothesis test, and this hypothesis test falls into the domain of statistical inference. So let's see some very simple ideas about the statistical inference. Uh, you uh, you have you are comparing two possible hypotheses that are opposing each other, and you want to show which one is representing the the current state of nature. So there are, what you want to show has always to be put into the alternative hypothesis. So you have a null hypothesis, H naught, and you have an alternative that is H1. And for instance, you want to show that a new vaccine reduces the number of infected animals in a population. Then you want to show that the probability, this pi is probability, so the probability of getting infected is smaller than the reference value. And the opposite is that the probability is larger or equal that reference value. Or you want to show that a new drug increases the survival of patients with this disease in the next 5 years. So the survival is larger than something, and the alternative and the null hypothesis is the opposite, that it is smaller or equal this value. Or you are in charge of a machine that produces tablets, and you want to show that it is producing with the right concentration. So the concentration is what you want to show is that the concentration is different than the reference value, because if it is different you have to stop the machine and calibrate it. And the null hypothesis is the opposite. So here we already have something that is that you may have heard, these one-tail or two-tails tests. So a one-tail test is one in which the alternative is using one of these smaller than or larger than signs. So in at some distribution that we will see later, you only have to look at one of the sides of the distribution. While in the two-tails test, you don't know if there will be a change, but you don't know if this change is because if it is an increase of the concentration or a decrease of the concentration. So you have to look in two tails of the associated distribution. So this decision is not innocent, and it has to be taken before doing the experiment. And very often you will be looking into one-tail tests because you want to show that the drug or your treatment is working in a particular direction, not in the other direction. And research hypotheses cannot use words like all, some, none, not all. And for instance, let's say that I formulate my research hypothesis as all hypertense patients benefit from a new drug, or no hypertense patient benefits from a new drug. The problem with this kind of a statement is that I would have to measure absolutely all hypertense patients in the world, because otherwise I cannot show that all or no uh, benefit. And here we understand the need for these false positive rates and false negative rates. So if you are not willing to have any mistake of this kind at all, then you will have to measure all the patients in the world. And research hypotheses cannot either be so ambiguous to this. Not all hypertense patients benefit from a new drug, or some hypertense patients benefit from a new drug. These statements are so vague that they convey very little information. So here it is where it comes the need for specifying the effect size and the statistical power. So you need to define how many, uh, uh, or not how many, but uh, what is the effect of the drug that you are analyzing. Okay, so yeah, and how many? So how many would be in terms of proportion? So you can do it with proportions. Okay, so what would be very often we were faced to what I call post-mortem analysis. So you design your hypothesis research, you collect the data, and then you analyze your data through an hypothesis test, and the data is not significant. And then when you look at the data, you realize that you didn't have enough power. So yes, now you know, but it is too late to know. So what is a safe analysis is to uh, calculate the number of samples that you need to have to be able to detect a given effect size, and then you're safe. And something it is a little bit counterintuitive in statistical inference is that you can reject a null hypothesis and accept alternative. You can fail to reject a null hypothesis because there is not enough evidence to reject it, and you can not accept the null hypothesis and reject the alternative because you would need to measure. So you can never accept the null hypothesis because you would need to measure absolutely all elements. This is like the all hypertense patients. So it is a bit like in legal trials. So the null hypothesis is the innocence of the defendant. So you can reject his innocence based on proofs. So that means I presume that you are innocent, but I have collected so much evidence against the assumption of innocence that I have to reject it, because all this evidence would be very weird if you're innocent. Uh, I can fail to reject his innocence, so I don't have enough evidence to show that you are guilty, but uh, it doesn't make you innocent. So it simply means that I don't have enough evidence. It is like in many trials with politicians and corruption and all this. I don't have enough evidence, but it doesn't mean that you are innocent. And but you can never prove the innocence, so you can never accept the null hypothesis. So because the problem for doing that is that I would need to collect absolutely all facts about the case, and probably I'm not able to do that, so, because of time, or because I don't have access to the information, or because I don't have a time machine to go back to in time and see absolutely everything that happened. So you can never accept the null hypothesis. In language, sometimes we are very loose about this, and we say we accept the null hypothesis, but in reality we should always say we cannot reject the null hypothesis. So the goal of hypothesis testing is to disprove the null hypothesis. That is why you put what you want to show, you put it into alternative, because you cannot accept the null, but you can accept the alternative. So by doing this, uh, uh, so and you disprove the null hypothesis by showing that if it is true, then all this information that we have experimentally collected would be very weird. So for instance, let's say that our null hypothesis is that all dices are fair, so they are not biased towards any phase, particular phase. And we have observed 5, 6 in a row. So what is the probability that this happens if a result like this happens, or even more extreme like this if the dices are fair? So this is the p-value. So the p-value is probability of observing this result, or something that is even more extreme than the result that we have observed. And then we compare this p-value to a threshold. This threshold is determined by the confidence level. This is 5%, and if it is smaller than 5%, then we reject the null hypothesis. That is something that we normally don't think about. So we think about a single test, but what happens if I make many tests? So let's say that you are looking for a compound that makes some that has some effect on a cell culture. So you will test 1000 compounds. Reality is that only 10% of them make a difference, and the other 90% they don't change anything in the cell culture. But you don't know this. This is why you're doing an experiment. So and then you do your experiments, and because you have false positive and false negatives, you will make mistakes. So out of these 900s, you will have a 5% of them that you have been unlucky with the samples, and then you think that they make a difference, but they don't. So 5% of 900 is 45. So these are the false positive, and the other 95% you were right. So you don't reject the null hypothesis, so there is no effect. And that was the real nature of real state of nature, so they didn't have any effect. On the other side, there are 100 compounds that make a difference. Let's say that you have a power of 80%, then 80 you will correctly identify, but you will miss 20. But all this state you don't know. That is why you do your experiment. All you see are the true positive coming out from all you see are the positives that come out from your experiment. So you see these 80 positives and these 45 positives. So in total you think that 125 compounds make a difference, but out of this, what is the probability that you are wrong? So 45 divided 125 of the cases are incorrect. So the probability of being incorrect, given that you have a positive result, is not 5%, it is much larger. This is what this Bonferroni correction is trying to decrease. So we are trying to decrease this 45 by making the 5% smaller. There are also some other tool to address this problem that is called the false discovery rate, and this false discovery rate correction. There are a few of them, and some of them are very easy to apply, and people doing many tests, like people working with microarrays where they test thousands of genes, or proteomics where they test again thousands of proteins, they are aware of and they use them. Okay, so let's look at how you will analyze your data. So to design your experiment at the sample size, you need to know how the data will be used. So let's say that you are an engineer that works for a pharmaceutical company. You are in charge of the machine that manufactures the tablets, and the tablets, you know that this is they have to put a concentration of 250 milligrams in each one of the tablets, but the machine is not perfect and it has a standard deviation of 1 milligram, and we will assume that the deviations from 250 are Gaussian. And then every week you take 20 tablets from the machine and you measure this week an average of 250.66 milligrams. So is this deviation of 0.66 milligrams significant, or so the machine is working incorrectly, or it is not? And in both cases it is important to know, because for instance, let's say that the machine is working fine but I stop it because I think that this deviation is too much, and then I stop it for recalibration, but during the recalibration time the machine is not producing anything, so I have stopped the machine for nothing, and it cost a lot of money to my company. So that has a high cost. But if I don't, but on the contrary, let's say that the machine is not working properly and I get an inspection, and then they show that it is not working fine, so then I would get a very high fine, and again it has a cost. So what should I do? Should I stop the machine or not? Then you delegate that decision into an hypothesis test. So your alternative is that the machine is not working correctly. That is what you want to show. And the null hypothesis is the opposite. That is what you want to disprove. And then let's think of the process to get this 250.66. So you will collect a tablet, and you measure this tablet. This tablet is because the machine, if the machine is working fine, they should be produced according to this curve, so they should be centered around 250, and the standard deviation would be 1. So the Gaussian goes from the mean minus 3 sigma to the mean plus 3 sigma. So they should be coming from here. So I get this one, and okay, I could have obtained another one, any one in this range, and then the expected value of a single tablet should be mu, so 250, if the machine is working fine, and the variability of this, the variance of this observation should be sigma squared, that is the variance of the machine. And now with just a single tablet, I have to compute what is the mean of my machine. So the mean, my estimate, that is why it has a hat. So with just one tablet, it is just the observation of that tablet. But because this observation is random, the mean is also random. And then if I repeat the experiment again, I will not get 250.5, I will get a different number. So my estimate of the mean will also be a different number. So the mean, the sample mean, your estimate of the mean, is also a random number, and if it is a random variable, it must have an expected value and a variance. So what is the expectation? If the machine is working fine, then the expectation, because mu hat is equal to x1, the expectation of mu hat has to be the expectation of x1, and the variance of mu hat has to be the variance of x1. So we will have the same mean and variance. So now a posteriori, what we have is this uncertainty about the mean. So we have we have to say, because we don't have any other factual evidence, that the mean is 250.5, and we have this uncertainty about where the true mean is. Now you collect a second tablet, and then this second tablet has this concentration to 51.8, and then your estimate of the mean will be the average of the two. Okay, so the mean is here, and how uncertain you are about that mean. Now you are a bit more certain because you have two tablets rather than one. So now the variance of this mu hat is a little bit smaller. So it is sigma squared, but now divided by 2 because you have two tablets. Now you collect a third one, a third tablet, that turns out to be here, and now you compute the average. The average, if you get an inspection now, you would be very happy because you are just on target. And now you have less uncertainty because you have 3 tablets rather than 2, and then you keep on collecting. So 4 tablets, 5 tablets, 10, 20 tablets. There is some mistake in this slide, so it should be divided by 20. And now, so you come out with your 20 tablets that are whose average is 250.66, but you have very little uncertainty about that about that mean. So you see that the machine working correctly, that is 250, is a rather uh, unusual result given this uncertainty. So it is very rare. It would be very rare that the machine is really working fine. Okay, so now we understand the process, but still you need to find a procedure to automate this decision. So if the tablets are Gaussianly distributed, then we have shown, or we have reasoned, that the estimate of the mean is also Gaussianly distributed with the same mean and a variance that is sigma squared divided by n. And then you need to find a calculation that you know how it is distributed if the null hypothesis is true. And this calculation is called a statistic, which is a very confusing name. And this statistic is something that a small calculation that you know how it is distributed. In this case, it is like this. So your observed mean minus the target mean, so what it was supposed to be, divided by sigma divided by square root of n. And this is distributed as a Gaussian with zero mean and standard deviation 1. Now you plug in your data. So I plug the data, and 250.66 minus 250 divided by 1, that was sigma, divided by the square root of 20. So I get a value 2.97. So if the deviation is as high as 0.66, this calculation set is as high as 2.97. Now I have to compute the p-value. The p-value is the probability of observing a value that is as extreme as the one I have observed if the null hypothesis is true. So 0.66 deviation translates into 2.97 in Z. So, but I know that Z is distributed as a Gaussian 0, 1. So it is centered at 0 and it has a standard deviation 1. So I should calculate what is the probability of observing a value that is at least as high as 2.97. So I take the 2.97 to the right, so this little blue area here, and it is as extreme to have a deviation of 0.66 or more, or having a deviation, a negative deviation of 0.66 or less. So I have to look on both sides. So 2.97 or more, or minus 2.97 or less. So that is why we have two tails. And now you understand our previous comment on having two tails or one tail. So on a two tails test, you have to look at some distribution, in this case the 0, 1 Gaussian. You have to look in two places, while in a one-tail test you only have to look on one side of the distribution. So you measure those areas, and those areas are 0.003, so it is 0.3%. So that means that if you repeat this experiment of taking 20 tablets and measuring the average in these 20 tablets, and the machine is working fine always, so if you repeat this experiment 1,000 weeks, then in 3 out of these 1,000 weeks you would see deviations that are at least as high as 0.66 milligrams on average. So on average 3 times every 1,000. Okay, and now with this p-value you have to take a decision. So your decision typically is to compare the p-value to a threshold. This threshold typically is 5%, and if it is smaller than 5%, then you reject the null hypothesis. And in biomedical sciences, we use multiple thresholds at the same time. So you use 5%, 1%, 0.1%, and you put a star. So you say if it is smaller than 5%, you put 1 star. If it is smaller than 1%, you put 2 stars, and if it is smaller than 0.1%, 3 stars. So our value is somewhere here in between, so you get only 2 stars. And it is important to say that the kind of tests that we do typically in biomedical research are significance tests. So you want to show that what you're measuring is different from a reference situation. But you might be interested in the opposite, so showing that what you are doing is equal to something. So this is, for instance, very used in equivalence or in the manufacturing of generics. So you want to show that the effect of your generic is equal to the effect of the reference drug, and showing equivalence is much more difficult than showing significance. So in science, we typically use significance. In genetics, for instance, they use equivalence. And the kind of calculations that are involved are kind of the same. So there are distributions, you have to look at one side of the distribution and so on. You have to calculate p-values, but the way these calculations are manipulated is totally different. And these are more similar again to the kind of science test that we do. So these superiority tests, non-inferiority tests, and they all have a small subtleties. So they may change completely, like this one, or there are small subtleties of difference between them. So this is an important message, just for you to be aware that you cannot, if you know one of these tools, you cannot extrapolate what you know immediately to all other possibilities. Probably they work in the same with the same intuition that you have from your known situation, but there are small calculation changes that you have to take into account. Okay, so what does it have to do, the hypothesis test, with the sample size determination? So we know how the data will be analyzed. So how do I use that knowledge to calculate my sample size? So let's summarize again the process to analyze the data. So you will define a null hypothesis. You know if the null hypothesis is true, you know that this calculation, this statistic, is distributed as a normal 0,1. And here you have the difference between the observed that this should be had. So the observed mean minus the expected mean. So the expected mean is 250. So this difference is called the effect size. So you have seen an effect of 0.66 in the previous experiment, 0.66 milligrams. And now you plug in your observed data, so 0.66 milligrams in this calculation gives 2.97, and you calculate the p-value associated to that. So the p-value is the probability of observing a value that is at least as high as the one I have observed, and because we don't know if it is positive or negative, we will compute it on both sides, and then we get this 0.3%, and then you compare this p-value to a threshold, and again this is a mistake, it should be 5%. So, and then you reject it. So this is how you will analyze your data. how does it help us to calculate the sample size? So we don't have when you are designing your experiment, you haven't observed yet the 0.66 milligrams, but you may have a target. So you may say, okay, if it deviates more than 0.5 milligrams, then I want to see it with a given probability of false positive errors. So now you have the effect size that is not coming from an experiment, it is coming from your design. So you want to detect this if it happens. It doesn't mean that it will happen, but if it happens, then you want to see it. So now you know delta. You also know, you need to know your population variance. So you need to characterize previously the machine and know what is the variance. And then instead of let's look at this. So I know that you will reject your p-value, the null hypothesis, if the p-value is smaller than the threshold. So let us go back to this curve. So I know that if the p-value is smaller than the threshold, you will reject the null hypothesis, and this threshold is 5%. So I know that you will look into both sides. So if the area on a single side is smaller than 5% divided by 2, you will reject the null hypothesis. So I can try to find what is the set value such that from that value to the right there is a 2.5% of probability, and that value is 1.96. So at this point, 1.96, the area, the blue area to the right is 2.5%, and the blue area to the negative side would be also 2.5%. So in total 5%. So I know that if your set is larger than 1.96, I'm sure that you will reject the null hypothesis. So I can put the threshold on the p-value, or I can put the threshold on set. So I can put the threshold on this 1.96, and that is what we are doing here. So I know that if your set is larger than 1.96, you will reject the null hypothesis, because the probability, your p-value, will be for sure smaller than 5%. So now I have everything. So I can compute, this is set. So this is set here. So set, if it is larger than 1.96, then you will reject your null hypothesis. So I have delta, that is what I want to detect. I have sigma, that is the population variance, and all I need is n. So you can solve for n, and this would be the calculation you need to do. So we need at least 16 tablets, because I cannot round down, because otherwise I would miss power. So n has to be larger than 15, so 15.4, so it has to be 16. Sorry, yeah, like this. Okay, so it has to be larger than 16. Okay, so now I have here a more general formula. It is almost the same. So this set 1 minus alpha half means, okay, so this is a nice notation. So it is a value such that from minus infinity to that point you have 1 minus alpha half of probability. So alpha was 5%. So alpha half is 2.5%. 1 minus 2.5% is 97.5%. So we need to find a set value such that from minus infinity to that point we have 97.5%. That is 1.96, and if to the left we have 97.5, to the right we have 2.5. Okay, so this is just a generic way to refer to this 1.96. So it is the set value such that from minus infinity to that value you have a probability of 1 minus alpha half. And then let's copy the rest of the formula, we have sigma divided by delta, so we simply copy it here. So let's see how this formula works, in which direction they are working. So let's say that I want to have more confidence. So I want to stop the machine only if I'm very sure that it is malfunctioning. So if I make this 95% larger, then the value, the 1.96, will move to the right, because I want to have, instead of this 2.5% of probability to the right, I want to have a smaller probability. So let's say only 0.5%. So instead of 2.5, we want to have 0.5%. So you could need to move this 1.96 to the right. So, and if you move this 1.96 to the right, this number will be larger, and the number of samples grows quadratically with that number. So if you want to be more confident about stopping your machine, then you need more samples. And what if my samples are more variable? What if the tablets, instead of moving with a sigma of 1, they move with a sigma of 10? Then it is much more difficult to detect a change of 0.5 milligrams. So if the sample variance increases, then the number of samples also increases. And the effect size, if you want to detect a smaller changes, so if instead of detecting a change of 0.5 milligrams, I want to detect a change of 0.1 milligram, I will need more samples, and so it goes to the denominator. It is interesting to see that all these dependencies are quadratic, so they grow quadratically with the changes that you are doing. And then there is a technical concept here, that is whether you are two-sided or one-sided test. So in the two-sided test, you need more samples. The reason is that the more information you put into the system, the fewer samples you need to test. So for instance, let's say that you have been working with this machine for 20 years, and you know that always when it malfunctions, it always goes in the direction of putting more concentration. It has never put less concentration. So all you have to do is to look on one side. So you would use one of these tests that we have here. So what you want to show is that the mean is larger than the threshold, and then that in this sorry, here. So you have to look on one side, and to look on one side, you still want the area to the right to be 5%, or the total area to be 5%, but because you don't have to split it into tails, so you will put it in one tail 5% to the right. You may remember that 1.96 had an area of 2.5%. So if I want an area of 5%, then this 1.96, I have to move it to the left. So I have to move it, I don't know, to 1.6. So now the critical set on which I will reject or not my null hypothesis will be smaller. So a smaller set, so now it has gone from 1.96 to 1.6, so it will result into a smaller sample size. Or the opposite, if you don't know in which direction it will move, then you will need more samples. If you know in which direction it will move, or you are wanting to show that it moves, then you will need fewer samples. So the more information you add into the system, the fewer the smaller the sample size. But it is only part of the story. What is the statistical power in this story? So we haven't presented it yet. So let's say that the machine is working fine, so the mean is 250. What I'm representing here is the uncertainty that you have about that mean. So you may remember it was the sigma was sigma divided square root of n. So let's say that the alternative, the true nature of the true state of nature is that the mean is 250.66, let's say. So now you would have this uncertainty around that value. So what is the probability that, so let's say that this is the null hypothesis, this is the true alternative. And the true alternative, you never know which one it is. That is what you are fixing with the delta that you take at the experiment design. So let's say that this is the true state of nature. So what is the probability that I don't reject the null hypothesis? So I have a critical value. So this critical value, it is the mean plus set 1 minus alpha half sigma divided by square root of n. This is simply, instead of solving for n here, we are solving for the observation here, so the mu hat. So this is my critical value. If my observed mean is not farther than this line, I will not reject the null hypothesis. And I can see what is the expression of this critical line if I'm coming from the null hypothesis. So it will be the mean plus 1 minus the set of 1 minus alpha half times this, or I can also express it as coming from the right. So when you come from the right, when you come from the alternative, this point is mu1 minus, and now we have a set 1 minus beta sigma divided square root of n. So what is the probability that I don't reject the null hypothesis if the alternative is true? So let's say that the alternative is true, but still there is a high probability that my observed mean, the mean of the 20 tablets, fall on the left side of this red line. So how likely that is? It is this area. So all this area under the black curve. So, and what I want is that this area is beta. Okay, so this equation here shows me what is how to reach this point from either you're coming from the null hypothesis or you're coming from the alternative. So what you want is that this value, when you reach this point, is smaller than when you reach this point coming from the left. And so you only have to solve for n, and then this is the expression, which is exactly the same one as we had before, only that this new term of statistical power has appeared. And here you have the other similar reasoning, but now when it is putting less than expected. So before we were putting the null hypothesis was here and the alternative was on its right, so the machine was putting more, but now it is putting less. And you make a similar reasoning, but at the end the formula for n is exactly the same. So this only happens for symmetrical distributions. There are not so many. Actually, the Gaussian is one of the few that are symmetrical. And here you have a representation of both at the same time. So this is the null hypothesis. If the observed mean is not further than these two critical lines, you will not reject the null hypothesis. This area here is 2.5%, this area here is 2.5%, and the areas of false negative are these ones, the black one here and the black one here, and each one is 20%. So if you have a power of 80%, then this area is 20%, this area is also 20%, so you don't have to divide by 2. And if it is a one-side test, then this is the situation. This area now is 5%, but still you have this 20 here. So how does it go now with the statistical power? Well, if you the new term is this one, statistical power. If you want to have more power means higher sets, so you will need larger sample sizes. And again, the dependence is quadratic with that. So as a summary, if you want to stop the machine with very low probability of false positive and false negatives, then these two numbers will be high and you will need a larger sample size. If you want to be very precise and detect very small deviations, the effect size will be small and then you will need a larger sample size. And if you have very variable observations, then sigma will be larger and then you will need a larger sample size. And if you can add a little bit of prior information so that you are looking only on one side, then the sample size will decrease a bit. And yeah, so instead of analyzing the probability of false positive, we can analyze the probability of false negative, and it goes with the same way. Okay, so let's stop it here, and in the next video we will make an example.